Hello. I think everything's ready. Okay, can you see the desktop? Do you hear me? Does it seem everything's okay?
Yes.
Yeah, okay, great. Thanks. All right. Okay, so today we're going to keep talking about higher order functions. Okay, so we're in this chapter, a third look on ML. It's got a variety of ideas in it. They're linked together. Okay, the other day we did this stuff on this other version of pattern matching, the case expression. Okay, so remember we talked about rules versus clauses. So we did that. The time before that we talked about function values and anonymous functions. We'll do a little bit more with those today. Excuse me. But what we really want to talk about is higher order functions today, and we'll talk about currying later. Okay. Higher order functions is a really important topic. This is one of the whole reasons for studying this ML is the way it uses higher order functions and the influence that higher order functions are having on modern programming. So this is one of the places where things get real interesting. Okay, so we're only going to actually be able to do an introduction to it, but this is actually like one of the starting points for really understanding like what people like about this functional style of programming. Okay, so we did some in class the other day. We did a real simple example of a higher order function. Okay, did this example here. Okay, all right. So okay, a higher order function is a function that either takes a function as an input parameter or returns a function as a return value. We're going to emphasize functions that take functions as input. So here was a function that took a function input. The h was the input to the function. Okay, see, so the function took that function as an input, and this one took two functions as inputs. Okay, down here you can see that we called the function with that function input and that function input. Okay, all right. Now, what I want to do today is start off with an example of a practical use. Like this is not, these are just meant to give you a sense of a function that has a function as an input. This is not especially useful here. This is not especially useful here. But I want to do an example that really is useful to give you a sense of a real important example of using a higher order function. Okay, so, oh, and these are functions that take functions as input. There's a lot of examples of higher order functions that take functions as input. There are much fewer examples of higher order functions that return a function. That is where the currying comes in. That's an example of a higher order function that returns a function. So that's one of the most famous examples of a higher order function that returns a function. So we'll do that next week. So right now we're going to emphasize higher order functions that take functions as inputs. And then when we talk about currying, we'll look at an example of a higher order function that returns a function as an output. Okay, so I've got an example here. Okay, here's an example called extreme. Okay, so here's a kind of build up to this example. We looked at how to find the max and min of a list. So there was the function we wrote when we were talking about recursion. This was an example of a recursive function. The max of an empty list is the negative infinity, essentially. If you give me an empty list, what number should I give you back for the maximum of it? Well, we talked about that the best answer to give is negative infinity. Then if you give me S for the max of a non-empty list, I use the predefined function that finds the max of two numbers, and I find the max of the first number in the list, and then my recursive function on the rest of the list. So my recursive function finds the max of everything else in the list, and then I use the built-in max function to find the max of that number and that number. Okay. Now, if this list had only one item in it, so this was the empty list, this would return max of the empty list, which would be negative infinity. And of course, one number is the maximum between the number of the max of this in negative infinity is going to be that. So we get the right answer for a one element list. That's why this thing should return negative infinity on an empty list, because then no matter what this guy is, if he's the only number in the list, if this is the empty list here and there's only one number in the list, it should be the max. The way this thing can be the max of whatever this thing returns is this thing must return the negative infinity, so that this number has to be larger than it. Okay, then here was min, exact opposite. Okay, right now I'm going to rewrite max and min a different way. Okay, here's another way to write max. It's got more lines of code in it. Okay, look at what it does. Okay, I'm going to give up defining max on an empty list. Okay, it's kind of weird. So you'll see why I want to do this. But if you give me an empty list, I'm going to say exception. Notice that I'm going to raise the empty exception. Now, that's the first time we've used an exception, but notice that if you take the head of an empty list, see how it raised the empty exception. See, uncaught exception, empty. So, some functions don't work on empty lists. Another example, if you take the tail of an empty list, see, you have an uncaught empty exception. Okay, so I'm going to use that. Okay, I'm going to use the fact that if you give me an empty list, I'm not going to even try to say what the maximum of it is. We'll see what normally this is the better thing to do, but we're going to see why I want to do it this way now. So I'm going to not try to find the max and min of an empty list. Okay, so then if you give me a one item list, well, that's the maximum. If you give me a list with two or more items in it, I'm going to compare the items and keep the larger of it. So if X is larger than Y, I put it back in the list and take the max of what's left. I've essentially reduced the list by one unit. I've pulled two things out and put one thing back. So the list has shrunk a little bit, but what I put back was the larger of the two. Okay, and then what that's going to do is going to take two things out, keep one. So the list is going to keep getting shorter and shorter and shorter until I get down to the one item list. My base case now is the white item list, not the empty list. Okay, I'll end up this is my base case. Notice that this is not a base case for the recursion. This one just says, okay, if you give me an empty list, I give you back, and I throw an exception. So the recursion ends on this one. Okay, then here's min. Again, empty list, I'm going to bail out, just throw an exception. One item list, obviously that's the smallest item in the list. If there's two or more items in the list, I compare them and keep the smaller one. Okay, so if X is the smaller one, I keep it and throw away the Y. Otherwise, I keep the Y and throw away the X. Okay, and then I ask for min of the resulting list, but this list is one shorter than the list I started with, so I'm decreasing the length of the list. Okay, now here's what's interesting. I repeated myself a lot there. That code looks a lot like that code. The only thing that changed was, okay, all the maxes became mins, and I changed that thing to that thing. That's all. Okay, switching from max to min was only switching this one little thing that compared the X and the Y. Now, this is a lot like your homework assignment when you did that assignment on insert. Essentially, we're duplicating the idea of that insert homework assignment. Okay, I want to make this into a higher order function that takes in as a parameter what kind of comparison to do. So I'm going to call the new function extreme, because it's going to find an extreme element. The extreme element might be the max, the extreme element might be the min, or it might be some other kind of extreme element. And it's going to take a function that we traditionally call it CMP for comparator. And the comparator is going to be the thing that does the comparing for me. So it's going to be the thing that decides what kind of extreme I'm looking for. Okay, right? So I'm going to say extreme with comparator. If you give me an empty list, I really don't know what to do. Now, this is why I bailed out on the empty list. in this case, since I don't even really know what kind of lists I'm working on, this is going to turn out to be a very generic function. There's really no hope of figuring out what to give, what the extreme of the empty list should be. Since I'm going to write a generic version of max and min, I no longer have this idea that, oh, negative infinity is the max of an empty list and positive infinity is the min of an empty list. That's only because I'm working with integers, so I kind of know what to do there on the empty list. When I want to make it more generic, I have to give up the thing. I'm gonna gain something. I'm gonna be able to write a very generic version of max and min, but what I lose is I don't know what to do on an empty list. Okay, so I'm gonna lose the ability to give you an answer for an empty list. So if you give me an empty list, I just throw an exception. Obviously, if you give me a list of one item, that's the extreme item. If you give me a list of two or more items, I compare them. And the idea here is this is a Boolean. And if it's true, X is the extreme item. And if it's false, Y is the extreme item. So I keep the extreme item and put it on the beginning of the list and do it over again. Notice it's the exact same function. The only thing I'm changing is, now notice here, this is written as an infix operator. Here it's written as a function. There's a little difference there. Okay, I'm switching. I could make this one an infix operator. I could have actually wrote this way, but I didn't want to. I'll show you. I didn't want to write it that way because it's a little bit more. It's a little trickier to work with that way. Okay, so I decided to leave it. I wrote it. I switched from it being an infix operator to being a function. Okay, so I'm making it a function. Okay. Now, the question is, how do I use these? We'll see in a second. Like I can still use these, though they're not functions; they're infix operators. Here, this one's written as a function, and it's written as a function on a pair. It's kind of important. I didn't write it this way as a function of two items. I wrote it this way as a function of a pair. Okay, it's kind of got to do with the way ML works. I have to write this as a comparison of a pair of items. Okay, right? And notice that when I call the function recursively, I have to keep passing along the comparator. Yeah, I don't make any change to it. It just kind of goes along for the ride. Okay, it's when the function is called, somebody provides me with a comparator, and then when I call the function recursively, I have to pass along the comparator. Notice here, I don't pass along the comparator. It's fixed to be that thing here, and it's fixed to be this one here. Okay. This is an example now of a higher order function. Okay. Now, let me type that into ML. Oops, didn't type in. Didn't. Okay. Oh, I forgot to put a semicolon at the end. Oh, I got something's goofed up. Oh no, I'm sorry. It was yeah. I wasn't reading real carefully. There's the type. It compiled. Notice that it's a very generic compare extreme function. The extreme function takes in, see, there's where it's a higher order function. One of its inputs is a function from a pair of A's to a Boolean. See, that's the comparator. Takes in a pair of A's. This function doesn't care what the A's are. Takes in a pair of A's. It needs to know whether, it is the first A larger than the second A or smaller. Essentially, is the first A the extreme one or is the second A the extreme one? True means the first one's the extreme one. False means the second one's the extreme one. Then it takes in a list of A's and it gives me back the extreme A. So it's very generic. And in fact, as it points out here, it's generic in two ways. It's a polymorphic function in two really interesting and important ways. First of all, it's polymorphic in the type it can take in. I can make A strings. I can find the extreme of strings. I can find the extreme of characters. I can find the extreme of integers. I can find the extreme of doubles. Okay, so that's the A part.
I have a question.
Yeah.
I'm confused what extreme means. Like, what if x and y are 1 and 2? Like, what is extreme of that?
Well, it depends on what kind of extreme I want. Do I want the extreme max or the extreme min?
So where do you specify that? Is that later on, or?
That's in this. Okay. Yeah, that's going to be later on when you tell me the details of what that comparator is. See, when you tell me what that function does, that'll determine. See, for example, that function could be this guy. Then it's finding the larger of them. Or that thing could be this guy. Then it's finding the smaller. Or that guy could be something else. We'll see some examples down here. See, that is the thing that determines how I'm finding extreme items. That's the other generic factor in this thing. It's got two kinds of generic, it's polymorphic in two profoundly important ways. It's polymorphic on the type of the list. I can work with lists of integers, lists of doubles, lists of strings, lists of characters. And then it's polymorphic in the sense that I get to decide how to find an extreme item. Let me give you an example. Suppose I want to work with strings. Okay, so I give you a list of strings. Okay, tell me, let's see. Tell me 4 or 5 different ways I could ask for an extreme item of this list. Start.
Just, I would say alphabetical, obviously, and
Okay, wait a minute. Right. Now there's 2 of those.
like the first letter.
Alphabetical, and there's 2 of them. What are they?
Well, like the whole string if it was alphabetically sorted, or if each individual item was alphabetically sorted.
No. Alphabetical, but there's already 2 of those. What are they? Two alphabetical extremes. What are they?
Do you mean like apple and pear?
Well, what are okay? Those are. What did you do there?
The A comes before everything.
So, what did you do there? Think, talk in use a precise language.
So A would be one extreme, and then pear would be the other.
No, that's not the right words. Be more precise still. So let me see what's he getting at.
Are you saying min and max?
Min and max, alphabetical order descending or alphabetical order ascending. Descending and ascending alphabetical order. Let me show you an example of that. Your computer is real smart. It can do all kinds of things. Let me open up my C drive. Where? Gosh, I'm not even. Oh, I know. Let me use it. Okay. Go to list view. No, go to the details view. Here I'm sorting by date. But what's this doing?
Just sorting chronologically.
But why am I getting 2 answers?
Oh, ascending and descending.
Yeah, ascending and descending. See the little arrow up there? Ascending and descending. What am I doing over here?
Just the same thing, but with
alphabetical. Notice that I have a list. Now, notice that this is very generic sorting. Windows is doing a generic sort here. I've got a bunch of items, and I'm sorting 4 ways right now. Ascending and descending on name, ascending and descending on when it was created. How did Windows do this? Did they write 4 sort functions? one for sorting names ascending, one for sorting names descending, one for sorting dates ascending, one for sorting dates descending. Oh, and then size. Oh, they have another two. See, do you think they wrote, how many sort functions do you think they were going to write? Do you think they're dumb programmers? Are they going to write one function that sorts names ascending, one function that sorts names descending, one function that sorts dates ascending, one function that sorts dates descending, one function that sorts sizes ascending, one function that sorts sizes descending? Does Microsoft want to waste its money that way?
No.
What does it do?
Uses what we're doing now.
Right, it wants a polymorphic sorting function like what we're trying to do here. It wants to find a way to write one sorting function that can then be parameterized in a lot of ways. Like here it's sorting strings 2 ways. Here it's sorting dates 2 ways. Here it's sorting ints 2 ways. 2 kinds of polymorphism: the type, string, dates, ints, and at least 2 different ways. Like strings can be sorted a lot of different ways, not just alphabetically increasing and decreasing, alphabetically increasing and alphabetically decreasing. So go back over here. Here's strings. We've got, I can sort this, or max, I can find the max alphabetical with pair being the max. I can find the pair is the extreme where I'm sorting descending. Or I can make apple the extreme where I'm sorting ascending. What else can I do? What other extremes can I do with those strings? Think creatively. What other extremes, what other sorts can I do on those strings?
The length of the string.
Yeah, I could ask for the shortest one of them. I could ask for the longest one of them. So I could sort those strings ascending by length and descending by length. Now there'll be ties, but there could be ties in alphabetical listing too. Yeah, and then you could ask for tiebreakers, and that's where things start getting tricky. Is to say, well, if I'm going to sort in a way where there's ties, what should I do about tiebreakers? If you go over here, an example, you can't. Can you have ties in this column?
No, they break up the folders and the applications. So you can't have a folder with the same name.
Yeah, you can't have folders with the same name, and you can't have files with the same name. You could have a folder and a file with the same name, but they break it up. They don't have a tie because all the folders come first and all the files come second. Okay, can I have a tie over in this column?
I suppose.
What do you mean, you suppose? Yes or no?
The file was created at the same time.
Yeah, of course I can have ties. They have to find a tiebreaker here. I don't know what tiebreaker they're using, but they would need to have some, or they could just put them in random order. Then you have, if you here you can clearly have ties, and maybe what could they do in the tiebreaker? What could be the tiebreaker?
Alphabetical order.
Alphabetical order or size, or they could just leave them random. Okay, they could just say, okay, tiebreaker, we don't care about what order they're in. What about size? Can there be a tie?
Yes.
Sure, 2 files can have the same size. And again, they could either have no tiebreaker and they just leave them in a random order, or they could give them a tiebreaker. They could go back to the name or the date. They could use if they have the same size, they could sort them by the date. They could use the date as the tiebreaker. Okay. All right. Now over here, I can sort these by, I can find the extreme in the sense of alphabetical order with where A's come, where A would be the extreme. Or I could find the extreme in alphabetical order where pair would be the extreme. Or I could find the extreme by length. So then I'd have a tie between cat and dog. Or I can find the longest, which would be orange. Okay. Now, what I'm trying to do is I want all those to be versions of extreme. I want this guy to be able to find the extreme of that. If that list is called, okay, if that's my list, I want to be able to find the extreme of the strings and I want to have a variety of comparators. Comparator one, yeah, I could have a comparator. I'll have a variety of comparators. Maybe comparator one does one kind of extreme, comparator two does another one, and comparator three does a different one. Okay, so I would have different comparators defined that would let me find the extreme element of that string. This one might be alphabetical ascending. This could be alphabetical descending. This could be length ascending. This could be length descending. Anything else to it? What else could you do? See, obviously with strings, you could compare them by alphabetical order. You could compare them by which string is longer or which string is shorter. Anybody think of another obvious way you could compare strings? You could do bizarre things like sort them on the second letter in the string. You know, you sort them by the second letter in the string, not the first letter in the string. Yeah, so essentially you drop the first. I mean, that's kind of a trivial thing to do, but it would be a different sort. I could have a comparator 5 that sorted the strings by their second letter, or I could sort. Oh, I could do a really weird thing. I could sort them in alphabetical order by their reading them like in Chinese from right to left. Okay, I could write that. I could write that comparator. I could write a comparator that compared from right to left, starting at that end of the string. That would be a kind of a challenging little assignment. But sort these in alphabetical order, but using the right end of the string to sort by. Okay, so that would be like the opposite of the usual alphabetical order, but start from the right hand of the string. I could write that comparator. It'd be a little bit of a challenge, but I could write it, and then I could sort this list. Yeah, and then cats and dogs would be the highest, and no, I'm sorry, cat would be the highest, and what was it? Apple and would pear and orange be the lowest? Yeah, I think. Yeah, so you can see yeah, the idea is to have things generically. I don't need to keep rewriting the extreme. Now I'm only having to worry about what the comparator is. I can get all the different sorts. I've got the generic extreme function. And now I'm curious about, oh, what are the different comparators? Now all my work is just going to be defining the comparators. And I can get all kinds of ways of sorting, or in this case, we're not doing, your homework assignment was to do insertion sort with a comparator. Here I'm just doing max and min, the extreme with a comparator. Okay, so the function's extreme, and whether it's a max or min depends on what this guy does. This function here doesn't really know what it's doing. Yeah, it doesn't know if it's sorting ascending or descending. It's just saying, if you give me a comparator, I'll compare two of your objects and tell you whether this comparator thinks that this is the extreme item or that's the extreme item. So the function is just going to go by whatever this comparator tells it. Okay? It keeps the comparator tells it which is the extreme item. True is meant to be the extreme item. False is the non-extreme item. So, well, true means that the first one's the extreme item. False means that the second one's the extreme item. Okay, so if this is true, it keeps the X. If it's false, it keeps the Y. So that's how you read this. It's meant to be that you make the function return true when you think this is the extreme one. This returns false when you think that's the extreme one. Okay, just like here and here. This is true when X is the larger one. This is true when X is the smaller one. Okay. All right. Now, this, like I said a minute ago, this is generic or polymorphic, kind of use those words interchangeably, in two profoundly important ways. It's polymorphic in the type of the list, and it's polymorphic in the way I compare the items. One of the polymorphisms comes from type polymorphism, and the other polymorphism comes from higher order function. Okay, so each of these programming concepts is giving me a form of polymorphism. Higher order, we spent a lot of time talking about type polymorphism. The type polymorphism is called parametric polymorphism. The technical term for it is parametric polymorphism, because this type variable is a parameter of the function. So the function's got this type parameter that says, oh, I can work on any type you want me to work with. As long as you can define a list of that type, as long as you can define a Boolean function of that type, I can work with it, okay? And I'll give you back an extreme of that type. So this is referred to as parametric polymorphism. The other kind of polymorphism doesn't really have a name. The polymorphism comes from the fact that I can change that function, so I could sort a list ascending or sort a list descending, or I can sort integers ascending or sort integers descending. So that polymorphism doesn't really have a name that I know of. It's polymorphism by higher order function. The higher order function tells this function, extreme, what to do. Okay, so that's a form of polymorphism by higher order function. So parametric polymorphism and higher order function polymorphism. Okay, all right. Now, the interesting thing now becomes defining these comparators. So the first thing we should do is, how do I get back this guy and this guy? Okay, here's how you do it in ML. You cannot pass that as a parameter to a function. That won't work in ML. If I go over here, ML is going to complain about being told that, oops, it didn't catch. Okay. Greater than is an operator. It's not a function. But ML has a really clever idea. There is a function in ML called op, which takes operators and converts them into functions. So the op function takes in a parameter, it's a higher order function. Op is a higher order function that takes in an operator and returns the function. Oh, here, let me show you. Let me do it this way. You know what op is? I'm sorry. You know what greater than is. Now, if you ask ML what greater than is, it gives you an error. Doesn't it? Because it's an infix operator, ML doesn't really like to work with it. But watch this. If I ask ML, what's op of greater than? It's a function from a pair of ints to a bool. It took the infix operator and turned it into a function on a pair of ints. That's why I had to use pairs over here. That's why I had to use pairs over here, because that's what ML turns these operators into. ML turns the operators into functions on pairs. It's an infix binary operator, and ML's op command changes an infix binary operator into an operator on a pair. Okay, and then I can do that with the other op on minus. See, the function's a higher order function. It took in an operator and it gives me back a function. Okay, so then I can call my extreme function. I can give it the operator less than, and then I can give it a list. Okay, I'm finding the minimum of the list. I can give it the other operator, and now I'm finding the max of the list. Okay, so I've recovered these two. But now here's something that ML says. This is what I'm showing you is actually, you haven't seen anything like this before, but this is unbelievably brilliant, the people who invented ML. Watch what you can do now. I don't want to have to call this to get max. I mean, it just seems really dumb to be typing extreme op greater than to get the max of a list. So here's what I'm going to do. I'm going to define a max function. What's the max function? It's the extreme using op greater than. Whoops. Oh, I forgot to say, I'm defining max to be See, I'm defining max to be extreme using op greater than. Okay. Max of see, I have a max function. And I didn't have to write it out like this. I could take this guy, and by telling him what see, this is called partial application. See, this function takes in two parameters, a comparator and a list. But ML lets you call the function with only one of the parameters. That's called partial application. So extreme given the op operator is essentially what we mean by max. Okay, now what do I mean by min? The min function is extreme with the less than operator. So now I've got min back. Okay, so now I've got max and min. I define extreme once, and then I get max and min as special cases of extreme. Okay, this is called partial application. The function takes in the name of the function, then the comparator, then the list. Essentially, I'm saying take the function and only give it one of its parameters. ML lets you do that. Lets you only give it one. Like Java and C and C++, you can never do this. The function takes in two parameters, and you call it with one parameter, you get a compiler error. The ML people were brilliant to think that this would be really useful. Okay, in C and C++, you can't do anything like this. But in ML, I can say, I can use this as a style of programming that lets me build functions out of partially applied functions. And ML people use this all the time. This is a real standard trick in ML. When I have a generic function like extreme, and this thing parameter, see, this is one of the ways of making extreme generic. So by saying extreme with a specific comparator, I've got a specific kind of extreme, and I can give it a name, like max or min.
Question.
Okay? Yeah.
So if you are using CMP, you have to, does that mean you have to pass in an operator?
No, I can write functions. I don't have to use an operator. No, and yeah, CMP is a function. Now here in this case, I got that function by taking that operator and converting it into a function. But I don't have to do that. I don't have to take an operator. I don't have to take an operator and convert it to a function. I can just write a function. We'll see in a minute, like an example of that. So I don't have to start with an operator and convert it to a function. For example, down here, suppose I wanted to take strings and compare them by their length. Okay, so here I'm going to call, here's a function longer that takes in two strings and then compares their length. So I compare the length of S1 to the length of S2, and I'm calling that longer. It returns true when this one's longer. It returns false when this one's longer. Okay. Then I'm going to use longer in a partial application of extreme to find a function called longest that returns the longest string in a list. Okay. Now there's no, see, this is a function, so this is not an operator. The operator is actually buried inside of that function, but this is a function of a pair of strings that returns a Boolean. Okay. So let's just do longer, for example. Here is longer. Okay. Notice it had to auto load the string class. So it auto loaded strings. So that's what that stuff was about. Okay. Now I'm going to use longer to define longest using an extreme. Okay. Now the longest, I've got a string array. I got a list of strings here, so I might as well use it. What's the longest string in that? Oh, I forgot. There's a missing quote over here. There's a missing quote there. Might as well fix that. And fix the missing quote. Okay, what's the longest string in that list? Orange. Okay. Now,
so you wrote the function longer. Can you go back to command prompt? So if you wrote the function longer first, and then you
then I gave it to
val
extreme.
longest equals extreme.
Yeah.
Okay, so you're passing in the function longer into your previous function extreme.
Yeah, I'm building longest out of extreme and longer. The extreme of longer is longest. It's you know, they call them higher order functions because it's a higher order of thinking. And believe me, I think I mentioned the other day, Google made billions of dollars thinking this way. Google, we're leading up to something called MapReduce, which is the heart of what Google does these days. They make all their money off of this thing called MapReduce. Okay. And we're building up to it. And MapReduce is a version of this higher order. Map is a higher order function and reduce is another higher order function. And they combined two higher order functions together into something called MapReduce. And it's what their millions and millions and millions of computers in their data centers do all day and night. They do MapReduce. Okay. So it's a higher order thinking. So I wrote longer, or I wrote extreme. So, you know, first I write extreme, which is very generic. Then but it needs to be told what comparator to use. So then I wrote longer. I gave longer to extreme as a partial application. So that says do extremes with longer, but I haven't given you the list yet. Okay. Then over here, then I gave it the list. I say longest. Now, longest basically is extreme longer of that list. And it can give me the longest element in that list. Okay. And, you know, I can go here and see, there was the longest string in that list. You know, I can just do some checking, put the longest one over here. See,
and then if you wanted to change your comparisons, like instead of looking for the longest, you want to look for the shortest, then you just write a function that's called shortest or whatever. And then
so let's see. There's longer. There's shorter. Okay. Now, val shortest is extreme using shorter. Okay. Now find the shortest of that string, of that list. Dog. Okay. And notice it could have been dog or cat. I don't have a tiebreaker. I gave it, okay. Now I made zeros the shortest string. Okay. Very generic. This is now, and then here I have a whole bunch of others ones. Like here's how I would sort strings alphabetically. Actually, there's already an operator for alphabetical order. It's in the string library. In the string library, they define greater than on strings to be alphabetical order ascending, and less than in that class. In the string class, that symbol represents descending alphabetical order. Okay, so I can take this. Okay, notice that I'm passing that directly to extreme. See, that's already been defined for me in the library. So there is a function that takes two strings and returns true when the first string becomes later in alphabetical ordering and false when the first string is earlier in alphabetical order. So that sorts strings. And let's see. It gets confusing. Think about which order. Well, let's just see which one that one gives us. Okay, so I'm going to take this thing. Okay. Now I can go, oh, forgot the semicolon. Oh, no, it's not. Now go to that thing there and say max string. Oh, I misspelled it. I forgot to capitalize string. I defined it with max string in camel case, and I forgot the, okay, pair was the maximum string. Okay. And if I go in here and put a Z in there, Z is the max string now. Okay. Right. So what did I do? I wrote extreme. Okay. Extreme takes the comparator. The library gave me a comparator of strings. So I feed it to my extreme and I get max string. And I take their other comparator and I feed it to my extreme. And now I can take mins, I can find the min string in alphabetical order. Okay, 0 was the minimum string in alphabetical order. If I get rid of the 0, then AAA was the minimum. Okay. If I put an X in front of that, then Apple becomes the minimum. Okay. So yeah, now I'm finding the extreme value in descending alphabetical order. Okay. Or no, yeah, descending alphabetical order. Okay. So this is a style of programming. It lets me write something very generic and then build lots of useful things out of it. And this is how if in the Windows operating system, this is all this sorting is going on here. Okay. Now let me show you where it's actually coming from. Like Windows is written in either C++ or C or something like that. Okay, right? So go to Google and Google Java 11 sort. Okay, in the collections class of Java 11, there's two sort functions. What is this? You sort of what we've been talking about. Can we see, how would you describe that sort function? How does it compare with what we've been doing so far?
Looks like it's, well, the second one's using the comparator, and the first one's not. So the first one is just either ascending or descending.
Yes, but what's there's something still there. There's still something polymorphic in there.
Oh, your list can be of any type.
Yeah, so it's got the parametric polymorphism. So it could be lists of any type T, and it's going to be default to either ascend. What it does do, it sorts in the ascending order of what's called the natural order of type T. Every type T has its own natural order, like the integers have a natural order, strings have a natural order. So this defaults to ascending order, ascending natural order, but it's polymorphic in T. Now, what about this sort? How does that, yeah, how would you describe that using the language we're learning?
It's polymorphic, and also you can add any comparator to it.
So it has what?
I don't remember the term that you used for the
higher order. It's a higher order function. It takes in a comparator function. Yeah, so it's got parametric polymorphism in the type of the list. So it could sort lists of strings, lists of integers, lists of student records. It can sort as long as you can give it a comparator. So it's polymorph. So this is how you could change it from ascending to descending sort. See, this one defaulted to ascending sort. If you want a descending sort, you'd have to switch to this one. You could give it the polymorphic list, but now you have to say, oh, and here's how I want you to compare, and here's how I want you to compare items. Okay, so this is polymorphic. This function is like our extreme. See, it's written in it's in the Java version of this extreme. It takes in a polymorphic list and a comparator function. Okay, now Java doesn't have anything like what we did with partial application. You can't call this function with just the comparator and then give it the list later. Java can't even come close to doing something like that. That's one of the really elegant things that ML can do. Once I have this function, I could say extreme, I go down here, extreme with that comparator, that's a useful function. The longest string in a list. Extreme with that comparator is a nice function. The shortest string in a list. Just like max and min really are versions of extreme. Extreme with the greater than operator is max. Extreme with the less than operator is min. Java can't do that. In Java, when you want max and min, you have to write them yourself. And what Java does is the max and min on ints is written separately. They don't get it from this. They actually just write it as a separate function. Okay. So Java, notice that they have the order here differently. I purposely had to make the order this way. I put the comparator, when I defined extreme, I made the comparator the first parameter so that I could partially apply it. So I could say extreme with the operator and not the list yet. So I purposely put the parameters, and this is important in ML programming. You think about the order of your parameters. So when I wrote extreme, I think about the order, and I think, okay, which order would be more useful if I'm going to use partial application? Well, what's more useful is extreme with a comparator, because that gives me something useful. If I put them in the other order, I could give extreme the list and then give it the comparator later on, but that's not a very useful idea. To give extreme the list first and the comparator later isn't very useful, but to give extreme the comparator first and the list later, very useful. That's what max is. And min. Max is extreme with the comparator, and min is extreme with the other comparator. And then I have longer and longest and shortest and longest and shortest, max string, min string. Oh, I can do this with characters too. Extreme with that comparator on characters will find the largest character in a string. This will find the smallest character in a string. Okay. So I can build all kinds of extreme functions out of this generic, this multiply generic function. It's polymorphic in the type of the list, and it's polymorphic in the first, in the fact that it's parameterized by a function, a higher order. It's a higher order function that takes a function as an input. And that function does some of my work for me. And I can change that as a parameter and get different results here. Okay. And now higher order functions go back a long way. Like here, Java has them. And let me show you, they even go farther back than that. Look up C QSort. Here's what a polymorphic function looks like in C. C makes things almost impossible, but this is what it looks like. There's the comparator function. See, there's comparator. Comparator is a if you've done some C programming, this is a function pointer. So this is a pointer to, comparator is a pointer to a function that takes in 2 pointers to void and returns an int. Now it doesn't return Boolean because C doesn't have Boolean, so it returns 0 for false and 1 for true. So the comparator is a function pointer. It points at a function. It points at a function that takes in 2 pointers, which are the 2 things that it's going to compare, and it returns an int 0 for this guy. Well, 1 means this guy's the extreme element, and 0 means this guy's the extreme element. Now here's the other remember, our functions are doubly polymorphic. Polymorphic in the list, and we have this comparator function. So we have a higher order function, and we're also polymorphic in this list. It can be a list of ints, it can be a list of it could be a list of ints, it could be a list of strings, it could be a list of doubles. Here's how C does the other polymorphism. Pointers to void. What that means is a pointer to a generic piece of memory. This function doesn't have a clue what it's pointing at, but it can point at anything. And it's up to this function to know whether it's actually pointing at an int or a double or a string. So C does parametric polymorphism by using pointers to void. That means parametric polymorphism existed back in the 70s, but it existed in an almost impossible to use way of pointer to void function pointers. But this is parametric polymorphism in its brutal, ugly form. This is parametric polymorphism in a really elegant form. ML really made progress in the history of programming. In fact, ML was doing this when C was doing this. They date from the same time. C was invented in the 70s. ML was invented in the 70s. ML came up with an idea that only now is starting to be realized how brilliant it was, while C was doing this. Parametric polymorphism using pointers to void. Okay. This is, there's almost no comparing how hard this is to work with how elegant this is. Now, you have to learn how to do this, but you have to learn how to do this too. Most of you have probably not seen C programming with pointers to void because it's considered advanced C programming. And this is this is ML program. This is not considered advanced ML programming. It's considered basic ML programming, but you have to learn it. You can teach this to people when you first teach them ML. If ML was the first language you learned, and people do this in a lot of schools, they teach generic programming like this in ML in freshman classes. If it's your first language, it's natural to be taught to think this way. There's no way in the world C can be taught this way in a first programming class. This is just way too hard. Okay. Pointers to void are impossible to teach in a first C course. Nobody can understand them. They're hard enough to teach in advanced C courses, but you can actually teach this to people in a first programming class. And you can also teach this in, the generics in Java, you can teach in a first class too. In a first programming class towards the end of the semester, sometimes some schools do get to generics. It's a little bit harder in the case of Java, but some schools do get to generics at the end of, say, a one-year course in Java, maybe like a one-year course in Java, usually like the data structures class. This would be like in the data structures class. Okay, this is just too hard. But the funny thing is, this was invented in the 70s, and so was this. The ML was invented in the 70s also. But the ML people were like light years ahead of the C people. Now, there's big differences, though. The C language could be used to write an operating system. You'd be hard-pressed to write an operating system in ML. It's not quite good enough in terms of speed to be used, for example, to program an operating system. So ML is very good, for example, data science. It's good for writing compilers. It's good for writing, it's really good for writing compilers. It's really good for doing any kind of statistics, data science, machine learning. It's really good for those things, but it isn't particularly good for writing an operating system. C, nobody uses C to do data science in it. Nobody's going to use C for, nobody would want to write a compiler anymore in C. Back then, they did write compilers in C, but eventually people moved away from C for writing compilers. People don't write compilers in C anymore. Usually they use a language like ML, maybe Java. But if you write an operating system, you're going to write it in C. If you're going to write something like an operating system or a file system or a web server, something that needs to be as fast as possible, then you still write it in C. Okay, so C is still the language for writing the lowest level, like device drivers, operating systems, database systems. Those things get written still in C because it's still the fastest language we have. Though Rust is trying to replace that. Okay, C is brutally hard to write code in. brutally hard to write code in, especially to get the code correct and not hackable. It's brutally hard. So even finally, we're starting to replace C with Rust, but Rust is also a hard language to learn. Okay, someday somebody would like to be able to write a compiler so good for ML that ML could be used to write an operating system. I don't know if that will ever happen. I don't know if ML will ever be good enough for writing an operating system in, but there are people who are trying to do that. They would like to see ML and languages like ML be useful for writing operating systems. But right now, Rust is the best language for writing an operating system. Okay, now let's see. Oh, here's another little trick. Here I wrote longer and shorter, then I wrote extreme in terms of longer and shorter. But in a sense, the longer and shorter functions don't have much use by themselves. So why did I have to find names for them? So here I used the anonymous function idea. Okay, this is where in this chapter we're talking about, there's this idea of anonymous functions. So here I'm using them in one of my higher order functions. I'm writing a higher order function and passing it an anonymous function as a parameter. This is how this stuff gets used a lot. I have a higher order function that takes in a function parameter and I give it an anonymous function. So let's look at that real carefully. Instead of saying longer is this, I'm just going to give extreme that anonymous function that says I'm a function that takes in a pair of strings and gives you back the Boolean of comparing the two strings. See, it's the right-hand side of this function without the name. That's the anonymous function. I remove the name from it, put fn in front of there instead of the name, and say, here's my comparator function. What that does for me is it eliminates the need for these two names. So from a point of view of my library, it's a little bit cleaner to do this. I don't have these names that don't really have a purpose. The longer function's not really useful. The shorter function's not really useful. It's longest and shortest that I'm interested in. So eliminate these two guys by defining longest and shortest in terms of these anonymous functions. Okay, that's a real common way to program. That I don't need to create names for things I don't need names of. If I don't need the name, like longer, just make it an anonymous function and make that the parameter to extreme. And then here's the other one. Make it a parameter to extreme. Okay, that's what I'm doing here. See, that was already defined for, well, here, these aren't anonymous functions. I'm passing the name of the function. Okay, so here, this is acting like longer here. See, there's the name of that function. Here, I'm just using a function that somebody else wrote. So I'm using my extreme and I'm using somebody else's function that came out of the library. Here, I'm using an anonymous function. Here, I'm using somebody else's function. Here, I'm using my function, but I don't really need that name. So I can eliminate the name by just using the anonymous function there. Okay, so that's another idea, that once I start playing around with higher order functions and they take functions as parameters, a lot of times the parameter will just be an anonymous function because they're usually short functions. Usually when you have a higher order function that takes in a parameter function, almost always the parameter functions are something simple. Yeah, here it just compares two things. It's very rare for a higher order function to take in some really complicated function as a parameter. That just doesn't come up in programming. Higher order functions usually take in simple functions, like a comparator, something that just compares two things. Actually, comparators are what pretty much invented this. The idea of a comparator, so you could write a generic sort or a generic extreme, that was one of the motivating issues in programming. People kept writing sort. I think I've shown, let's look in a different part of the Java library. Here's an older piece of the Java library. sort byte, sort char, sort double, sort float, sort int, sort long, sort short, short object, sort object. See, yeah, back in the, somebody started saying this is not a good idea. There's nothing generic here. Well, there is a little bit of, there's nothing generic here. There's nothing generic. Sort an array of byte, sort an array of char, sort an array of double. Here, you're just allowed to say what part of the array to sort. So you can say sort from this index to this index. That's not very generic. It's a little bit generic. This thing sorts from the beginning to the end. This thing says, oh, I can sort between here and there in the array. Okay, but look, sort byte, sort char, sort double, sort float, sort int, sort long, sort short, short object. Finally, down here, here's the generic version of sort, which was added years later. For a long time, this is what Java was. Then, it doesn't say when this was added. This generic sort was added. Oh, I wish it said. Sometimes they tell you when it was added. I think it was Java 5. I think, if I remember, I think it was Java 5 when they added the generic sort, but it was much later. This is what motivated trying to come up with better styles of programming. Now, ML had generics back in the 70s. Java in the 90s still didn't have it. Java didn't get generics until around 2005 or something. It shows you how long it took this stuff to reach from the world of ML into the world of Java. I mean, Java has it all over the place now. Generics are a huge part of Java now. But this legacy stuff still sits around there. You can see it in the library. Like here, you just see it all over the place. Like there's the copy array of bool, copy array of bytes, copy an array of char, copy array of double, copy array of floats, copy array of vignettes. Some intern had to take that copy and turn it into that copy and that copy and that copy and that copy. My guess is that was work done by an intern, okay? Because somebody had to rewrite copy over and over and over and over and over again. There's nothing generic here. It is, if you look in the source code, it's literally written out all this many times. That's not a good thing. Okay, so one of the motivating things in the last 20 years of programming language theory was to try to get rid of nonsense like this, get rid of this kind of stuff and move towards generics. The funny thing was, this was been sitting there staring them in the face since the 70s. Like Java C did it this way. Okay, and C also has all those different sort functions for sorting an array of ints, sorting an array of doubles. Then they also have this generic one. So they have both here's the overloaded ones, and then there is a generic one on an array of T. And there's two kinds of generics in Java. If you go back to the sorts, and this is part of the legacy of Java. See, this is one kind of generic, sort an array of objects. That'll work on anything because anything is an array of objects. That's the old-fashioned Java generics. Then this is the modern Java generics with a type parameter. And it got the type parameter from ML. So originally Java generics would look like this. Oh, you're sorting an array of objects. Okay. And then it's up to these guys to know how to compare themselves. And then it's up to them to see, it's going to compare sorting in the natural order of the elements. So it's up to these things to know how to sort themselves. And then Java came up with the idea of giving a type parameter. So it's an array of T's, and you could pass it a comparator of T's. Okay, you can pass it a comparator. So this was added way later. It doesn't say when it was added. I'm pretty sure it was Java 5. It took about 10 years for Java to go from this to this. This was there from the beginning. This was there in the original version of Java. A really bare this array of objects is pretty much the same thing as this pointer to void. Just like an object can point to any, a a reference of type object, whoops, a reference of type object can point to any object. A pointer to void can point to any object. So pointer to void is the C equivalent of the object class. It's the pointer that can point at anything, just like this is the reference that can refer to anything. So Java using object is not much better than C using pointer to voids. Okay, so back in the time when C was invented and Java was invented, they were pretty much doing the same thing. Pointer to voids in C, object references in Java. Really crude form of polymorphism. Then eventually, well, C never got parametric polymorphism, but C++ has it. So there's a Q sort in C++ that looks like this modern sorting in Java, parametric polymorphism. There's the parameter, an array of type T, where I can make T see anything I want. There's the parameter. I can make T an array. I can make this an array of colors or array of strings or array of employee classes, objects. Okay, so there's the parametric polymorphism. This is just weird polymorphism. This is just weird. The trouble with this is, when you do this, and I say array of string, that is an array of strings. The compiler makes sure that's an array of strings. Suppose I have this, and I want it to be an array of strings. The compiler will let you put a color in the middle of that array because it's an array of objects. Now what happens is, in the middle of your array of strings, there's a color object because somebody goofed up. Your sorting algorithm will crash when it hits the color object, because the sorting algorithm thinks it's got an array of strings, and it will literally crash when it hits the color object. And this style of programming was really error prone because the compiler cannot force the array of objects to only be an array of strings. So back in the day of this style of programming, programs would occasionally crash when somebody goofed up and stuck the wrong thing in an array. And the compiler would not stop them from stuffing the wrong thing in an array. This happens in Python and JavaScript all the time. Over here, if I say an array of string, there's no way anything there's no way anything but a string can end up in that array. The compiler will say, you told me an array of strings, so I will only let strings be put into the array. So when it compiles your program, it checks at compile time that the only thing being put in the array are strings. So your program's way safer. And that's how ML works. When you say that this is, well, ML, you don't even say what this is an array of, and ML figures it out for you. ML says this is a polymorphic array. See, I don't even have to put in the type parameters. It puts them in. ML is, again, the beauty of ML is when I define that function, ML puts the parameters in there for me. Notice in Java, I have to write this code with all the parametric, I have to write the code with the parametric polymorphism in there. And it's a little bit tricky. When you write this code, look at how complicated that comparator is. That says I'm a comparator of anything that's a superclass of type T. Okay, so I can compare anything that's a superclass of type T. It's really it's actually kind of tricky. In ML, ML figures all that out for you. ML just says you have a comparator of type A's and you have a list of type A's. And there's not, I don't even have to put that in my code. I don't have to say that. ML figures it out for me. That's way better. This style of programming is tricky to do in Java. It's a little bit tricky to write this code because you have to really line up a lot of things with these. You have to know how to read all these kinds of things here. Generic programming in Java and C++ is a little bit cumbersome because it doesn't work as nicely as ML does. Okay, ML puts the type parameters in for you. Java forces you to put the type parameters in, and you got to put them in right. And it's really easy to get this messed up when you write this kind of generic code. ML in the 70s figured this out. Java's still trying to get it right. Okay, and it's actually important to realize, if ML figured it out in the 70s, why didn't people just use it? that's a hard question to answer. Partly is because the people doing this were so mathematically based that a lot of programmers weren't paying attention to what they were doing. And they just didn't appreciate it because it was kind of couched in the language of a lot of mathematics. And it took a while for like Java and C++ programmers to realize that what these people were doing was real relevant to them. You know, if you go back and look at stuff written in the 80s and 90s, people thought this was kind of just weird abstraction. They thought it was just being kind of weird. And it took a little while for them to realize that, no, it's real important. You know, and then Java and C++ absorbed this stuff. But because it was tacked on to the language years after the definition of language, it got tacked on kind of in a cumbersome way. So whereas ML puts the type parameters in for you, C and Java and C++ make you put in the type parameters. Okay, so now what we've done is one kind of higher order function, and then we're going to look at some more examples of higher order functions next week, and then we'll do this thing on currying. Okay, so we'll do some more examples of higher order functions next week. We'll do the map reduce examples I mentioned. We'll look at this example, map reduce. Sorting is a real good example of higher order functions, and map reduce is a real famous example of higher order functions. So we'll look at those next week. Okay, and I'm trying to convince you that ML is not an extreme weird language. Yeah, trying to get you to realize that the stuff that these mathematicians, these really theoretical programmers came up with back in the 70s and 80s is, you know, more and more people are realizing that they were really on the right track, that they were really coming up with very good ideas. It might look abstract, but you know, I'm getting a lot of mileage out of that little bit of code. I'm getting an awful lot of comparisons out of that little bit of code, and I'm not writing crazy stuff like this. You know, that's not good. Sort, 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 sort. That's just not good. If you look in the library and you look, you just see block of code after block of code after block of code that look exactly alike. Just one uses ints, one uses doubles, one uses shorts. You know, that's not good. Languages need to move away from that style of programming towards this kind of stuff here. Okay, so we'll quit there, and there'll be another programming assignment. Maybe over the weekend, I'm going to have a programming assignment for you about higher order functions. That'll be up there. I'm writing it now, so there will be a homework assignment 5 up there in a few days, and then it'll be due in a couple weeks. But you might check back. I hope it'll be up there in a couple days. And assignment 5, making use of higher order functions. Okay, so we'll quit there. And anybody got any last second question? Anybody got a question? Okay, I'll put these examples up on the website. You know, they're not up there yet. The examples we did today, I'll put them up there. And so they're tricky. You know, I cannot overemphasize how important these ideas are, but they are tricky. They're not simple. Okay, it's not, you know, not much code, deep ideas. Short code, deep ideas. Okay, all right, so we'll quit there. Have a nice weekend. Bye.